A very good morning, afternoon, or evening to everyone. My name is Kenneth, and on behalf of my co-authors, it is my pleasure to present our work as part of this special session on signal processing and neural approaches for soundscapes. Our work concerns an automatic method to choose appropriate sounds, otherwise called maskers, that can be added to real-life urban acoustic environments as a noise mitigation strategy called soundscape augmentation. The method aims to pick maskers to optimize values of subjective indicators such as the overall pleasantness of an acoustic environment. The main novelty of the method lies in a probabilistic approach to model the inherent randomness resulting from subjectivity. Combined with attention-based deep neural networks in our validation experiments, our approach can allow models to perform better than if they were trained with a standard mean square error loss function. In short, as the title of the presentation suggests, it is a neural probabilistic approach to automatic masker selection for urban soundscape augmentation. With that, let me provide an overview of the presentation. The timestamps for each section can be found in the video captions. Firstly, I will detail the background and motivation for our work, and discuss some other studies related to ours. Then, I will introduce our proposed method and describe the experiments we carried out to validate the method. Lastly, I will present the results of the validation experiments and conclude the presentation with some possible directions for future work. Our work takes place in the context of soundscape augmentation, where we consider a soundscape as an acoustic environment as perceived by a person or people in context. This is in accordance with the definition provided by the International Standard for Soundscapes, ISO 12913. The definition emphasizes the perception of the acoustic environment, so augmentation thus implies the addition of maskers to existing soundscapes to change their perception. For example, we could add the sound of a bird to an existing soundscape beside a noisy road to improve its overall perceived pleasantness. This addition can be done via any number of means. If our noisy road were present in real life, we could, say, add the sound of the bird using speakers placed near the location itself. The basis for the study of soundscape augmentation techniques lies in evidence showing that traditional decibel-based metrics don't necessarily correlate well with perceptual indicators. For example, this graph shows the results of a study conducted by the World Health Organization, where they investigated the percentage of people considering the soundscape at a road as highly annoying as a function of the sound pressure level (SPL) at the road itself. Each point corresponds to a road, and we can see at most a weak quadratic correlation between the variables, with huge error margins. For example, roads with sound pressure levels of 65 decibels could highly annoy anywhere from almost nobody to almost 60% of people. Hence, there has been a move towards perception-based approaches to complement traditional noise mitigation measures where human responses are involved. Soundscape augmentation is just one of them. Existing soundscape augmentation approaches generally use a variety of sounds either generated or recorded. With the available variety, a natural question then arises. How do we choose optimal maskers to bring about a desired perceptual change? We know that this depends on the masker itself, the existing soundscape that we are potentially adding the masker to, and the relative sound pressure levels or relative SPLs between the two. As an illustration of the dependence, assuming the same masker and generally unpleasant soundscape, as the masker SPL increases, the perceived pleasantness of the combined sound may increase as the masker distracts the listener away from the soundscape. However, beyond a certain point, the masker SPL becomes so high that it is perceived as noisy and unpleasant in itself, and the perceived pleasantness drops. Unfortunately, this curve is different for different maskers and different soundscapes, and we usually only know this based on post-hoc analysis, after listening tests have been conducted with a variety of maskers and soundscapes. But fortunately, there has been much work to develop prediction models for perceptual attributes of soundscapes such that they can be used to choose optimal maskers before or even without any listening tests. This brings us to a short discussion on related work regarding such prediction models. Prediction models are relatively varied in the literature, and there have been a host of studies using methods ranging from linear regression to deep neural networks. These prediction models usually take in raw audio, spectrograms, or psychoacoustic parameters computed from the audio in order to predict ratings on subjective scales such as the perceived pleasantness, eventfulness, loudness, and so on. However, these existing models are largely deterministic in nature, in the sense that the same raw audio, when used as input, is always mapped to the same predicted value on the rating scale. This treats the subjective ratings as ground truth labels, but there are usually inherent uncertainties in the subjective ratings themselves due to factors that cannot be reasonably controlled, such as the listener's current stress level or noise sensitivity. Hence, probabilistic models that can account for or model these uncertainties may be useful in representing the subjectivity in perception and thereby make predictive models. There is some evidence for this in a study performed by Mitchell and colleagues, where they attempted to represent soundscapes as areas in a perceptual space, as shown in the diagram on the right of the slide. Our proposed method lies in a similar vein. We adopt a probabilistic approach by training a neural network to predict a distribution across possible ratings. We refer to the neural network as a probabilistic perceptual attribute predictor, or PPAP for short, and it is part of an overall automatic masker selection system, or AMSS for short. The AMSS essentially aims to use the PPAP to decide which masker in a set of masker candidates M of k will maximize the value of a perceptual attribute when added to an existing soundscape S0. The attribute can, for example, be the perceived pleasantness, which we will use for this study. At inference time, the system first takes as input the existing soundscape S0 as an audio recording and, of course, has access to the set of capital K masker candidates. It iteratively augments the existing soundscape with maskers to produce augmented soundscapes S of k, and then feeds the augmented soundscapes S of k into the PPAP, which in turn returns the conditional distribution of pleasantness ratings given the augmented soundscapes it is presented. For this study, we use a normal distribution characterized by the mean mu of k and variance sigma of k squared, and the PPAP outputs just two values that characterize the distribution. The prediction of the ground truth pleasantness for the augmented soundscape is then made by drawing from or transforming the distribution returned by the PPAP. The AMSS then collates the predictions across all masker candidates and chooses the best masker M tilde as the one with the highest predicted pleasantness when used to augment the existing soundscape S0. The best augmented soundscape is then made by actually performing the augmentation in the inference or deployment context. Now, this begs the question of how we should train the PPAP, since the output is a distribution and not a simple deterministic value. We will need not just pleasantness ratings Fk of the augmented soundscape S of k, but also a loss function that is derived from the output distribution of the PPAP. This probabilistic loss function that we propose is the log probability of the ground truth pleasantness f of k given the output distribution. For this study, since we are using a normal distribution, this will simply be the log probability that f of k is observed under the normal distribution with mean mu of k and standard deviation sigma of k, as shown in the equation for j on the slide. Now, it remains to validate this against a standard method using the mean squared error loss for a deterministic regression model for pleasantness. The corresponding expression for this loss function is shown as jdet on this slide, and a model trained with jdet predicts mu of k exactly for the pleasantness f of k of any augmented soundscape. As an ablation study, we thus investigate the performance of model predictions using the probabilistic and deterministic loss functions across a variety of model architectures. The common dataset used to train all models is one that we curated ourselves. The dataset contains 12,600 unique sets of subjective responses to augmented soundscapes in a 5-fold cross-validation set, as well as 48 additional sets of responses in an independent test set. The augmented soundscapes in the cross-validation set and the test set are of course disjoint. The responses were obtained via a large-scale listening test involving about 300 participants, and the ground truth labels for pleasantness are the subjective ratings for pleasantness obtained in accordance with Part 2 of the International Standard for Soundscapes. These are so-called ISO pleasantness values, but from a statistical point of view, we can just treat them as ground truth labels taking on values in the closed interval from -1 to +1. For further information on the dataset and how we collected the responses, you may refer to our manuscript. Alternatively, you may also access the link on the slide or scan the QR code to access the spectrograms of the augmented soundscapes and the corresponding responses that form the dataset. As for the PPAP model architectures, we first converted all raw audio of the augmented soundscapes into log-mel spectrograms with 644 time bins and 64 mel frequency bins. The log-MEL spectrograms were then used as input to convolutional recurrent neural networks, or CRNNs. And the general architecture is shown on the bottom right of the slide. The CRNNs have a variable feature mapping block, and for our validation experiments, we vary it to have one of 4 possible configurations. One configuration is a vanilla block consisting only of bidirectional gated recurrent units, but the other 3 consist of attention mapping blocks with additive, dot product, and multi-head attention. After training all models over 10 runs using a 5-fold cross-validation scheme, we used the model weights with the best validation loss for evaluation in both the cross-validation set as well as the test set. The evaluation metric used for comparison is the mean squared error, or MSE, between the ground truth and predicted label, and a summary of the results is shown on the table on this slide. As a reference, we also provide the results of a trivial label mean model, which is a deterministic model that simply predicts the mean of the labels in the training set regardless of the input. As expected, all other models trained in the validation experiments performed better than the label mean model, with MSE values below 0.1556 on the cross-validation set and 0.1181 on the test set. This indicates that the models did indeed extract useful features for prediction. In addition, the test set MSEs were also lower than that of the cross-validation sets. This is possibly because the test set was smaller with 48 responses, as compared to the cross-validation set with 12,600 responses. Furthermore, for the 4 architectures tested, the models with probabilistic output performed better than the same models with deterministic output. This is true for both the cross-validation set, as shown in the red boxes, as well as the test set, as shown in the green boxes. To quantify the significance of these reductions, we computed the percentage reduction in MSE between the deterministic and probabilistic models, and performed 2-sided Wilcoxon sign rank tests using the results of the 10 runs to determine if the reductions were statistically significant. Model architectures with a significant improvement, at least at the 5% significance level, are denoted with asterisks on the table. In particular, the reductions in the test set MSEs for the PPAP without attention and PPAP with additive attention are statistically significant and provide evidence to support the generalizability of our proposed method to unseen data. However, the lowest improvement in the test set MSE was actually observed in the PPAP with multi-head attention block. Since the PPAP with multi-head attention block already has about 50% more parameters than the other 3 models, with about 120,000 as compared to about 80,000, this could have caused the trained models to be overfitted to the dataset regardless of whether we used the deterministic or probabilistic loss function to train the model. Now, I would like to summarize our main contributions in this work and suggest some possible avenues for future work based on our study. In this presentation, we have described an automatic masker selection system using a CRNN-based probabilistic perceptual attribute predictor. Based on models used to predict ISO pleasantness, the PPAP with various feature mapping blocks achieved lower mean squared errors in prediction when trained with our proposed probabilistic loss function as compared to the standard deterministic loss functions. We have also generated a dataset from the large-scale listening test that we conducted to successfully validate our proposed method, and we have made that available online. Future work could investigate if the performance improvement indeed carries over to other perceptual attributes such as the eventfulness, calmness, or perceived loudness of augmented soundscapes. In addition, the validation experiments were carried out only using the dataset we collected in a digital fashion. Ideally, the predictions should also be validated with real-life environments where maskers are added to in-situ soundscapes, in order to confirm if the proposed method is realizable or, as we say, ecologically valid in in-situ contexts. Lastly, since the primary assumption underpinning the PPAP is that of random ground truth labels, it could conceivably be applied to any context where predictions of subjective evaluations are desired, even outside of the realm of soundscape augmentation. With these ideas in mind, I hope that we can pave the way to more signal processing and neural approaches for soundscapes, and of course to more human-centric perception-based approaches to soundscape augmentation. Thank you so much for your attention, and I wish you a pleasant day ahead.